Hello all. Let's look at how we can explain light using electromagnetic theory. So, historically speaking, electromagnetic theory was a breakthrough in physics, right, an understanding of light in general, because the theory really brought in two different fields together. So, one is electricity and the other one is magnetism. So, this was done by Sir James Clerk Maxwell, right. So, in about 1864, right, so he proposed this unifying theory. He said, let us take electric energy and magnetic energy, and these things are together, right, they are coupled, right, and when they are coupled you can explain the whole spectrum of waves at that point of time, primarily looking at electricity as separately and magnetism, and then we had light, right, which was coming from a completely different direction. All right. So, this unifying theory created a breakthrough, right. And why this theory is one of the breakthroughs is because it was able to explain everything that was already out there, right. That is one of the important requirement for a unifying theory. So, whatever we understood about light, it was able to explain, but further it was able to explain things like polarization very clearly, right. So, polarization is an important property of light, right, and it made even better, right, understanding of some of the phenomena. All right. So, that is the reason why Maxwell proposal was really appreciated, and still we use these theories, right, and we constantly evolve in understanding how material interacts with light and how one can manipulate the properties of light using this electromagnetic understanding of light. Okay. So, let us look at what is that magic equation and why we are so excited about using this electromagnetic theory or field theory, right, to understand light. All right. Let us look at that. So, the electromagnetic theory actually couples as I mentioned, electric field and magnetic field, right. And there were coupled equation, right, that was proposed, and those equations were the following. So, del cross H equals dou D by dou T plus J, del dot E equals minus dou B by dou T, and then you had del dot D equals 0, del dot B equals 0. So, this is the wave or let us say symmetric partial differential equations in a medium, right, without any charge or current. Let us say this is a dielectric medium, right. So, if it is a dielectric medium, this is what you see. So, E is the electric field, right, which is represented by this. This is nothing which is represented in unit wise volt per meter, right, and H again as a function of position and time, amp per meter, and D is the displacement current, which is nothing but coulomb per meter square. B is similarly represented by Weber per meter square. All right. So, this is how proposed this whole coupled equation. This was not new at that point of time, right, because this is basically the Ampere law, and this is the Faraday, this is Ampere, this is the Faraday, and this is Gauss basically, right. So, he coupled all of this and said this is the beauty of the proposal. So, when it was thought that the Ampere law and Faraday laws only was applicable to electricity and magnetism, the whole beauty of Maxwell's is to bringing this together, right, in order to represent the energy or in this case waves, right. So, D is represented by epsilon E plus P. So, where epsilon is the permittivity, right, E is the electric field and P is the polarization density, right. So, this is nothing but polarization density, right, Coulomb per meter, right. And similarly you can represent B as mu naught H plus mu naught M, right. So, M is nothing but magnetization density, which is amp per meter, all right. So, mu naught and epsilon naught probably this is all free space permittivity and permeability that you might have already studied in your basic courses, right. So, we do not have to go into details of that, right. So, this is how you can represent an electromagnetic wave propagation, right. It's nicely done, but then you want to know how much energy this wave is going to carry, all right. So, that is what you want to do. Let us say I take a simple volume right here, and I want to know how much of energy that this particular volume is going to handle or carry, whichever way you want to call it, right. So, the electromagnetic energy now is carried by both magnetic field and the electric field, right. So, both are carrying this energy, right. Let us see how one can find the energy or power or energy density that these waves could take forward. Okay. So, the way that one could understand is by looking at the space that you want. Let's say optical power. So, how you can use optical power? Let's take this Maxwell equation that we already know, right. So, these two guys, and then we are going to do some manipulation here. So, let us do it here itself. Okay. So, let us multiply E dot del cross H, right, and then H dot del cross E, right. So, if we do that, then it becomes E dot J plus E dot dou D by dou T. Similarly, we get H dot dou B by dou T. Should not forget the negative sign here. Okay. So, now we can use the identity, right. So, basically what we are trying to do here is optical power, right. So, how much power that the wave will carry, right. So, that is an interesting thing to do. So, by using the identity, right. So, basically the identity is B dot del cross A minus A dot del cross B can be represented as del dot A cross B. So, this is the identity, right. So, if we use this identity, right, you can apply it to the above equation, right. And if you do that, this is what you would get, minus del dot E cross H equals to E dot J plus E dot dou D by dou T plus H dot dou B by dou T, all right. So, this is what you would get, all right. So, what do we see here, all right. So, if you look at this equation, right, you will quickly notice that this is something that you must have encountered earlier on in your electromagnetic courses or in your introductory course in photonics, that this is nothing but your Poynting vector, right. So, E cross H is nothing but the direction, right, of your energy flow, right, and E dot J, right. So, E is the electric field and J is the current that you have, right. And what is this? This E dot J, right, is nothing but your power basically, right. This is voltage times similar to VI, right. So, this is similar to that, right. So, this is actually the energy that actually the power that we use in our conventional electric circuits, right. So, let's move on and then see how we can rearrange this, right. So, E dot J is basically your the power density, right. So, your okay. So, your power density is basically E dot J, all right, and the way that we could rearrange this is not sure whether we are using small j or capital J, it does not really matter. Okay. So, now if you rearrange it, right, so it will become del dot E cross H, right, minus dou by dou t epsilon naught by 2 E square, okay, plus mu naught 2 H square minus E dot dou p by dou t plus mu naught H dot dou m by dou t. So, all we have done here is bring in the expanded form of D and B, right. So, you want to use our earlier definition of B and D here, and you can expand it this way. And now this tells us how the energy should be, right. So, what should be the energy or what should be the power density of this, okay. So, this is basically power density or energy density if you would like, all right. So, now let us closely look at these factors, okay, what they actually represent, all right, and what is the significance of this, all right. So, let's do it one by one, all right. So, this basically is the Poynting vector that we already know, all right. So, so S is the Poynting vector, right, and that is nothing but E cross H, right. So, this is, it represents the instantaneous magnitude and direction of power flow, right. So, this is telling you the magnitude and direction of the power flow. So, we know electric field and magnetic field are orthogonal to each other, right. So, if we represent like this is x, y and z, let us say your electric field and magnetic field are in this direction, right, let us say E and H, right, and your energy flow should be perpendicular to this. So, the energy is going to move in this direction, all right. So, that means when you have oscillation, when you have field, right, oscillating in H direction, right, and then when you have field oscillating in x direction here and y direction here, then the wave should move, or the energy should be in the direction of z, right. And this is how waves propagate, right. So you have oscillation in xy plane, but then the energy, it will be moving perpendicular to this, okay, either into this screen or out of the screen, okay. So this is what the Poynting vector actually tells us, all right. The scalar quantity here, right, this is the scalar quantity, meaning this thing, right. So whatever you have, let's look at that. So what is that? So this scalar quantity, right, is a unit energy per volume, right. So let's say this is U, right. So this U is nothing but epsilon naught over 2 E squared plus mu naught over 2 H square. So what is this? This is basically energy density stored in the propagating field, okay. So this is energy density in the propagating field. So this is a very important quantity, right. So it consists of two components, as you can see here, right. So this is the electric field, right, or the electric field component and magnetic field component, right, at any instant of time, right. So this is where the energy is actually stored, right. So this is the stored energy of the propagating wave, all right. And let's move on, right. So this is the first factor is done and the second factor is done. Now we know what this factor represent. Let's look at the third factor, right. So what is the third factor? So third one is, we call this as let's say UE, right. So which is E dP over dt. So what is this? This is power density, right, extended by the electromagnetic wave on the polarization, right. So you are putting a certain energy for polarization of this, right. So energy spent for polarization. So you spend this energy for the polarization right, of the atoms inside the medium, right. So this is energy spent, all right, inside the medium, all right. So okay, if, there is a little correction here. So the negative sign is this way, all right. Oops. So let's look at the third factor here, right, or the final one, the fourth factor here. So that is UM, right, and UM, as you have guessed, this is mu naught H times dm over dt. So what is this? So this is nothing but energy or the power density extended by the electromagnetic wave on the magnetization. So this is energy spent for magnetization, right. So if you look at the composition of this equation, right. So this is the power density that we saw, right. So the magnitude and the direction of the power, right, is represented here, right, and then the energy stored component at a given point of time, and then this is the third quantity here represent energy spent, right, in the medium, all right. So the energy spent in the medium is very medium dependent, right. So whether what is the magnitude of polarization and what is the magnitude of magnetization that one has in the material. Nonetheless, this energy is spent, okay. So overall when you look at this whole equation, right, the power density equation, it's basically conservation of energy. So conservation of energy as it propagates through a medium, right. So we saw we took a a small volume that we had here, right. But then when energy is when the wave is propagating through this, right, there are a couple of things that can happen, right. So how much energy is taken through this material, that is represented by these two, the first two factors, right. But then the third factor that you see here is going to be spent on the material itself, right. So you can say that it's kind of loss or work done on the material. Okay. So this is the way that you could find what is the power density of a wave, or how much power a wave can carry, right, as it propagates through a medium. All right. So so once we understand this, we can use these properties in order to discriminate various loss mechanisms, right, when the wave is traveling through a medium as well. So you can use this for characterization as well, particularly when it comes to material that are dispersive and material that are non-dispersive. Okay. So those are all the things one can utilize to understand how much energy or optical power a wave could carry. Okay. So with that, this part is covered. Let's look at what is the effect of wave if it is a very simple linear and non-dispersive medium, right. Let's look at that rather quickly. Okay. So you can take it from here, right. So if it is a linear and non-dispersive, so if it is a linear and non-dispersive medium, you can write E dot J will be equal to minus del dot E cross H minus dou T 1 by 2 E dot plus 1 by 2 H dot B, right. And basically this is the total energy that is being carried, right. This is the total energy density. All right. So when you take an optical field, right, where J is 0 and also let us say M is 0, right. So this is a linear non-dispersive medium. If that is the case, let us say an A around a closed area A, right. So one can use this to find out how much is the power density. So that means you are going to do let us say with around U dV plus at the power that we had, let us say U E, right, dV, all right, because the magnetic component is 0. So we are only looking at the electrical part alone here, right. So using this we could quickly find out how much of energy we have, right, in any closed space or in any volume that you are interested in. Okay. So it is just deduction from the general equation that we saw here. So this is more or less a comprehensive general representation from here based on whether you have magnetization or not, right, what is the degree of polarization and so on. You should be able to find out the energy in the system. All right. So with that we understand how a wave could carry energy inside the system. And when it is propagating through a medium, right, it's the medium properties also influences the energy that you are going to carry. It's not that when you put the optical field into the medium, all the power is going to go through, right. So the field is going to interact with the material, right? And that is where your polarization and magnetization property of the material comes in. Most of the material, the magnetization is 0, right. Most of the energy that you spend is for polarization of the material that you have. So that is energy spent. So you are going to spend some energy there, and what you have left over is what you are going to transport through the medium. Okay, and this energy that you are spending on the polarization, right, also depends on certain properties of the material itself, right, because the polarization is not again a single constant number, right. So it is again a series, right. So probably when you think back, right, you will write polarization as an expanded series, right. So you will have linear factor, and then you have square and cube, right, as a function of electric field. So it will be chi 1, chi naught, or chi 1, chi 2, chi 3, right. So chi 2 times E squared, chi 3 times E cube, and all those. So chi's are nothing but your susceptibility that is actually creating your polarization. So when you spend energy to the polarization, eventually you are going to lose that. And it also depends on the electric field strength, right. And when you have very low electric field, you will only spend the linear loss there. So you will not have sufficient E squared and E cube magnitude, and that will avoid all these energy losses, right. And there are a lot of other interesting effects that would come in when you have E squared and E cube terms become significant. Alright. So with that brief understanding, now we know how the energy propagates, right. In the next lecture we will see how to understand the solution to this wave equation, right, and also a polarization, right. Let's look at that in the next section.